Okay, so we're all very excited, I think, at the moment because we're kind of embracing a new age of computing. It's kind of a new parallel age. Here I've just got an example of a chip that you can buy off the shelf. This was released about 4 weeks ago. It's called an Easy chip, Tile MX100, and it has 100 cores on one physical chip. And this thing is available to buy. I think it costs something in the range of about $200 to $300, so it's actually very cheap. As you can see here, it's got kind of the physical chip, if you like. It supports up to 100 cores. There's various different models of this. You can get kind of 50 cores, 70 cores, 100 cores, whatever you like. It has, and also the cores are quite, I mean, they're x86 cores, so they're not lightweight cores at all. They're real cores. It has huge amounts of cache. So the total chip has something like over 40 megabytes of cache. And it also has quite a few number of dedicated devices, such as accelerators, network control units, and it supports quite a substantial amount of memory, kind of something about a terabyte of RAM. So these things are available to buy. They're cheap. They support huge amounts of parallelism. So what's the problem? Well, there's kind of another dimension to this problem. So this is kind of the CPU only. This is the x86 challenge. So there's another challenge on top of this. That's this increasing kind of awareness of these accelerator units. Here I've got some examples. This one here is a GeForce graphics processing unit, kind of things that are very good for games. 10 years ago, but they've kind of developed quite a lot from that. Now they're used generally for lightweight processing. They're very good at floating point arithmetic and things like this. Another one, for example, here is the Ultra Stratix. It has something like 10 teraflops of power. It's absolutely enormous amount of power you can get from these general purpose units. They're also very cheap. So they cost somewhere in the same region as the Easy chip that I showed on the previous slide. So kind of in the range of hundreds of dollars. So for hundreds of dollars, you can get teraflops of power. It's really, really quite frightening when you think about it. 10 years ago, this kind of thing was almost unimaginable. And now we have so much computing power, we don't know what to do with it. This one is quite an interesting arrangement here. Can anybody see from the slide what these devices are? It's probably not that clear. They're PlayStations, yes. So this is, I think this was the largest supercomputer 5 years ago, something greater than 500 teraflops, and it's comprised exclusively of PlayStation 3s. Something like 1,700 PlayStation 3s. However, it's kind of not a free lunch. So these hardware accelerator chips have been around for a long time now. But the problem is programming these things are incredibly difficult. In most cases, you need to be quite an expert. So you need to have lots of low-level expertise. I'm talking things like low-level programming models, Opencl, CUDA, possibly P-threads on top of that, so a lot of C, a lot of hacking involved. You need to know quite a lot about the architecture. So what does the architecture do? How do things fit onto the architecture? How does it execute these things? On top of that, you've got how do you parallelize your application? So assuming you've mastered these techniques, how do you go about actually parallelizing the thing you're trying to parallelize in the first place? That's quite difficult. And then on top of that, how do you know that when you've parallelized it, it's the most efficient parallelization for your algorithm? It's almost impossible to tell, I'd say. And then what happens if you change? So you go from a GPU to a paralleler or something like that. You have to completely redesign your application from scratch, almost, to deal with that. So this is incredibly costly. Just getting people who are appropriate experts in this domain, but also training people It's an extremely time-consuming and costly process. I think just doing this in a trial and error approach exclusively is just not going to work. So just randomly hacking systems to get them to work in parallel is not the way to do it. That's what I'm going to talk about today. So one thing we've been working on in St. Andrews is a concept called a parallel pattern. I'm sure this concept is quite widely known to a lot of people. It's been around for a long time. So essentially the idea of it, it's kind of like a function. So in Erlang you can think of this as like a nice higher order function. But what it does is it implements a parallel behavior. So here I've just got two examples of these types of parallel patterns. The one on the left here is called a farm. Think of this as like a data parallel operation. So the idea is you've got some pieces of work and you've got some computations or functions that you want to compute over that work, and you want to do them in parallel. So that function is replicated. It could be replicated over an architecture, over a number of CPUs, or whatever. The one on the right here is called a pipeline. It's a slightly different type of parallel pattern. The things in the boxes here are what's performed in parallel. So, for example, you can think of this as like a conveyor belt with some robots. So here you've got a factory that's making cars. The first robot puts a door on a car, the second one the engine, third one the gearbox, and so on. So the parallelism comes from this, that each robot can work on a separate car at the same time. So you get a kind of parallelism in a streamlined way rather than it being data parallel. And of course you can nest these, so you can put a pipeline inside a farm, so you can have each worker of a farm being a pipeline, and so on. You can have farms nested inside pipelines, and so on. The great advantage of this approach is it's extremely high level. So most application programmers, they don't have to think about all the technical details. All the implementation of the parallelism is hidden away. It's provided by the pattern. They just need to think about how they're going to make their application fit the particular pattern. So this is a nice functional way of thinking about parallelism. Okay, there's no low-level details, no Opencl, no spawns, and all of that kind of stuff. So what we've done is we've implemented a parallel pattern library in Erlang. So everybody can go away and download this. It's free. We have a website here called skel.weebly.com. So the name of the library is called Skel, short for skeleton. Very imaginative name. It's basically a library of skeletons for Erlang. It has quite a number of different skeletons there, and they're growing all the time. So as people are providing us with new types of applications, we're adding new different types of patterns to that library. The general API of it is very simple. So this is kind of the top-level API of the Skel library. What it does is there's a top-level function called do that takes a skeleton tree. So the programmer simply just describes what type of skeleton he wants to use, whether it's a farm, whether it's a pipeline, whether it's a nesting of farms and pipelines. So he basically just simply expresses this in terms of an Erlang tuple with some atoms. Very simple. The input items are basically the tasks that he wants to work on in the pattern. So these could come from a list, they could come from messages being sent in, and so on. And then the result of the parallel computation, if you like, the parallel pattern, is the output. And so again, this could be a list, or it could be streamed. So it could be messages sent out from the pattern. So it's very simple to use. So what we're going to do today is I'm going to talk about using these patterns for programming heterogeneous systems. So that's architectures comprising of a CPU and an accelerator of some kind. So we have our patterns. We need a couple of little more tools and techniques up our sleeve, if you like, to do this. So one of those techniques is we're going to use some Opencl bindings for Erlang. These basically provide functions that execute Opencl from Erlang. So they basically just wrap Opencl, so you can call them from Erlang. They provide things like marshalling, so you can give it an Erlang binary and so on, and it will do all the marshalling between the Erlang side and the Opencl side. So it will just convert everything for you. Things like functions to copy to and from the accelerator memory. It enables Erlang programmers generally to write code for accelerators. But one important point here is this alone is not enough. This doesn't simplify programming. This is incredibly complicated to use. So what we're going to do is we're just simply going to use this, but we're not going to use it directly. I'll explain that in a short while. Using this library, you basically need to write as much code as you do with C. So you may as well just use C. This offers absolutely no benefit to an Erlang programmer using this directly. Another tool that we're going to use is a refactoring tool. I think everybody probably has heard of refactoring by now. One example of a refactoring tool for Erlang is Wrangler. And what it does, here we've got a screenshot of the tool. It allows people to basically restructure their code in an automatic way. So if you have a text editor or an IDE, a refactoring tool allows you to do some transformations on the code. Things like renaming, moving functions around, adding parameters to functions, this kind of thing. But the transformation step is done automatically. So the code is transformed automatically, and the tool will check all the conditions, all the side conditions for you. So it will check whether the transformation can be applied, whether it's going to break the code, whether, for example, if you're renaming it to a new function, whether the new function is going to change the semantics, if it's going to conflict with any other names, and all this kind of stuff. So the refactoring tool will do all that checking for you, and then it will automatically transform the code. So an example of a refactoring tool in Erlang is Wrangler. This was developed by Simon Thompson. I don't think he's sitting here at the moment, but he's around in the EUC if you want to talk to him about it. It handles the full Erlang language, so it's not a toy tool, it's a real tool you can use. Very important in these tools, it's faithful to things like the layouts and the comments. So the refactoring tool, it doesn't introduce code that suddenly looks weird or suddenly looks incredibly complicated. It tries its best to match the idiomatic style of the programmer as best it can. It has an undo feature, which is very nice. So if you make a mistake, if you choose the wrong refactoring, you just go back and it will just reverse the change. It's built in Erlang, which is nice. It makes it very easy to apply to itself. It's kind of a technical detail, but it's quite nice. And this is just a screenshot here. So here is an example. It's just Emacs. It runs in a variety of different editors. I think there's an Eclipse version, a VI version, and possibly several others. This is the Emacs version. The programmer simply just has code here, like he would normally in Emacs. He might select a bit of code of interest, and then there's a menu here, refactoring menu, that provides quite a number of different things you can do. You can't quite see them from the slide, but things like renaming and function arguments and things like that. So we've built on top of these, we've built on top of the patterns and the refactoring tool, and we've created a new framework called Lapedo. This picture here, I'm guessing probably nobody has seen this picture before. Every time I ask this in a talk, everybody always looks with blank expressions. Does anybody know who this is? Apart from Kevin, of course. Sorry? No, it's not related to anyone in the room, I can assure you. So this is a skeleton that they found in the ice. A team of Italian scientists found a kind of almost completely preserved skeleton in the ice. What was interesting about him was that he was a mixture of modern human and Neanderthal. So he was a hybrid skeleton, and he was called Lapedo. So we thought it was a nice name for our framework of hybrid skeletons. We called it Lapedo. So what Lapedo does, it extends our skeletons, our Skel library, with hybrid skeletons. What I mean by hybrid is skeletons that allow CPU, GPU, accelerator computations to be mixed together. So you can do offloading and things like that. It builds on top of all these libraries, so it just sits on top of the bindings for Opencl, CUDA, interfaces to Opencl code. And then on top of Lapedo, we have new refactorings that do several things. Firstly, they allow the introduction of these skeletons automatically. So you can use a refactoring tool to basically introduce all of this code into your Erlang program. We'll do it completely automatically. You can do things like you can switch between a CPU and a GPU operation. Things like code generation, so all of that stuff I talked about before about marshalling, calling the Opencl, using these bindings. Refactoring tool will just generate all of that for you, so you don't even need to touch it. And we have an implementation of this in Erlang. It's on GitHub, so if you want to go ahead and download this, please do, and tell us all the bugs that exist. We'd love to hear from you about that. So talking about these hybrid skeletons, what are they all about? So I talked briefly before about these patterns, like farms and pipelines. Well, a hybrid skeleton is quite simple. It basically extends the idea of a pattern, but it adds in a new kind of component. So this component in pink here, that's what we call a hybrid component. So this is something that can operate on a GPU or some kind of accelerator. And what the hybrid pattern does is it allows you to mix operations that run on a CPU and operations that run on a GPU together. Okay? So it allows you to mix these operations together in one single pattern. Okay? And then it works in exactly the same way as it did before. So here, the farm, you've got some tasks coming in. You simply replicate how many CPU and GPU operations you have, and then the parallelism is handled for you automatically. So there's one slight thing I want to add here. This is part of a general framework called Party that Melinda will be talking about tomorrow. Part of that work. It's kind of like a one-stop shop for parallel programming in Erlang. Contains absolutely everything you need to write parallel programs in Erlang. Contains things like program shaping. I'm going to talk about this very briefly in a moment, so don't worry too much about that. But generally, it means refactorings to change the structure of your program so that you can start to parallelize it. So it's like a pre-parallelization step. Then it has pattern discovery, which Melinda will talk about in a lot of detail tomorrow. It's like a Google of parallelism for Erlang. It kind of finds all the parts of your Erlang code where you can then introduce skeletons or parallelism parts. And then it's got the refactoring, which introduces the patterns. And then on top of that, we've got Lapedo, which then allows you to do the GPU and CPU offloading on top of that. So it contains absolutely everything you need in one package. So this is what Lapedo looks like. So here we've got kind of a diagram here with a user here on the left-hand side. Up the top here, this is what the user has to provide to the framework. So he provides his sequential Erlang application. And in the pink, he has to also provide a kernel. And this is just, at the moment, he has to do this. So he provides an Opencl kernel. And then what Lapedo does is he uses Wrangler to firstly shape his code a bit to make it so he can introduce these skeletons. And then once he's done that, he simply introduces the appropriate refactoring he wants. He introduces a skeleton he wants via the refactoring tool. This gives you a CPU application, and then he uses the GPU code generator in Lapedo, which introduces all the marshalling code to get the kernel up and running. And then once he's done that, he simply basically refactors it again to make it hybrid. So once he's got a shaped CPU application with the GPU code, he then further refactors it to get a CPU and GPU application. So it's just a few clicks of a button. You go from a completely sequential Erlang program to one that will run on a CPU and a GPU almost completely automatically. Okay. And then once he's got that refactored program, this hybrid thing, he can then run it on his architecture at the bottom. His architecture could be a mixture of whatever he likes. So let's just talk a little bit in depth about each of these stages. So the program shaping step is the first thing he needs to do. These are things like it shapes code so you can introduce parallelism. This can be things like converting data structures to make them more efficient. It can be things like removing dependencies from code, because you can't have dependencies when you run things in parallel. It doesn't work. It could be things like breaking up ETS tables to avoid collision of read and write accesses to things like that. So a whole host of different types of things. So this is the first step he has to do. Then once he's done that, if he provides a kernel, the Lapedo framework will then generate all of the wrapping code. This is things like all the boilerplate Opencl wrapping, calling the kernel, marshalling the data to and from the buffers, etc. So the Lapedo framework will completely generate this, and it will also generate all the code to offload the computations to the GPU. Then after he's done that, he can then simply start introducing the patterns. So once he's got this code generated, he can use a refactoring tool to introduce these hybrid skeletons into his shaped Erlang program. So he does this via refactoring tool again. This results in a hybrid application that uses accelerated components from the previous step. So the code that was generated from the previous step, the Lapedo framework will basically pick that up and link it into the pattern automatically via the tool. So this process is what we call semi-automatic. Semi-automatic in the sense that the programmer has to do a little bit of guidance. So he has to choose which refactoring he wants, he has to choose which pattern he wants, but it's automatic because all of the conditions are checked by the tool automatically, the code is transformed automatically. So he doesn't really have to do that much. So I'm going to show you just an example of how this works in practice. Now this example is called N-body. It's an application from physics, basically. It's used to work out how particles interact with each other under certain forces and things like that. So it's a simulation of how particles interact under an influence of some force. We have a sequential version of this in Erlang that we take. And at the moment, the programmer has to provide an Opencl kernel. So we're kind of working on generating that automatically. But at the moment, he just has to provide it. So this is what the main part of the code looks like. It's very simple. So it's basically some kind of recursive function that does some mapping of some computation N-body 1 over some particles. So it's quite the high-level structure is quite simple. If we delve into it a bit, it looks a little bit more complicated, but the thing we're interested in is this N-body 1, because this is going to become our worker. This is going to be the thing that we're going to execute in parallel when we're going to introduce the hybrid patterns. So the user basically takes this, he writes an Opencl version. It's probably quite simple to translate that directly to Opencl. There's nothing complicated about it. He then does some program shaping. So firstly, he does some things like he changes some data structures in his program. So he changes the lists into binaries. This is just to make it, so he removes all the copying overhead when he's going to do the hybrid offloading. This is a refactoring step. He basically just selects the high-level function and says, make this binary, basically. Sorry, Costas? So your question is, why would I do that? Well, there's a number of reasons why you'd want to do that. Firstly, you can't send list items to a GPU. They have to be in a binary form. The second one is the overheads of lists in Erlang is massive because you're copying all the time when you send them to devices. So you want to eliminate that. So by introducing binaries, you introduce the copying overhead, and you also allow the data structure to be marshaled across to the device. Makes sense? You still look puzzled. Okay. Yep. Because this particular application, it's a list. So the programmer provides it as a list. He could miss this step out if he wanted to. He doesn't have to perform this step. I'm just showing an example of one of these program shaping steps. That's all I'm doing. So the user could have up front a binary version. That's absolutely fine. Then he can just completely skip this step altogether. It's not a problem.
The point is it might be necessary in order to allow some parallelization. There are other things to its Chris' point.
The second step after the program shaping, after he's done some kind of restructuring of data and so on, is to generate all of this Opencl marshalling code. So this is just an example, quite cut down actually. If I was to fit all of this code onto a slide, it would be about 15 slides of code. So I decided not to do that. So this code is completely generated. So all he does is provide the kernel. It looks at the kernel, looks at the arguments, looks at the types of the arguments, and then it just generates all of this code. You can see it's quite involved. It's got things like setting up. It has to load the kernel. Things like it creates a load of buffers with certain types, whether they're read or write only, all this kind of stuff. And then it calls the kernel here, and so on and so on. So it's a lot of boilerplate code. You really don't want to be writing this stuff yourself. It becomes very messy, and you can the amount of errors you can introduce in this code is absolutely astronomical. So you really don't want to be doing this yourself. Then once he's got that, he basically simply refactors his code. So he takes that function nBodyPar, and he introduces a hybrid farm. And then the refactoring tool introduces this code you see here. It's got things like number of CPU workers, number of GPU workers. I'll tell you a little bit about how this information is derived in a moment. And then it thinks, so this is what a Skel pattern looks like, by the way. So here you've got an atom here that describes what pattern you're using. Here we're using a hybrid farm. And the farm takes two types of workers. It takes a CPU worker, and it takes a GPU worker. So the first one is the CPU nBody1. The second one is the hybrid version, the GPU version. So this is generated automatically from the previous step. Then you have to do some other things. You have to do some tagging of the data to know which tasks are going to be sent to a CPU and which are going to be sent to a GPU. So one of the things is no point just sending all your data to a GPU or all of your data to a CPU or completely randomly distributing it. That's not going to do you any favors at all. I'll explain that shortly why. So what we do first is we profile our data. So if the skeleton will do this automatically when you run it. So it will take your data. It will create a profile of what that data looks like. So whether the data is CPU bound, whether it's GPU bound. And it does this basically by some profiling, running samples of the data on the devices, calculating performance, memory usage, this type of thing. Once it's got a profile of your data, it will then create an optimal scheduling of that data onto the device. So this is an example of how that schedule looks like. So the things in the red here are GPU cores. The things in the blue are CPU cores. I've just put in here, the brown is basically other accelerator devices. So Costas gave a very good talk before about using parallella. Sorry, I didn't know your name, but Magnus, sorry. Magnus and Costas both give a talk. Magnus mostly. A very good talk. I just wanted to show that our framework could sit on top of that. So you're really not constrained to a particular type of device. If you have a way of running code or offloading code, you can simply plug it into our framework. So this here just shows an example of a distribution. So the red is the GPU core. The green squares are tasks that the scheduler has decided are optimal to run these tasks on a GPU to get the best performance. And the rest, it's going to optimize them on the remaining CPU cores, dividing them up based on some profiling or on some metric. So this is done statically. So this is done before the parallel pattern is running. So it does it up front. This is just an example. What happens if something changes? So an application changes, an instance of it changes, your data changes, your architecture changes. Well, all you have to do is reprofile or rerun the skeleton, and it will come up with a new optimal configuration, a new schedule for those tasks. So you can see it'll change. So let's say I've added 2 more CPUs to my architecture. It'll work out that the best way to distribute them possibly could be as follows. So this is an optimal or a near optimal configuration. So here's just some results we've obtained from this Lapedo framework. This is an example of the n-body like I showed you before. This graph here basically shows the CPU-only code. So the way to read this is along the bottom here is the number of CPUs we have working in the pattern. So 1 here up to 24. The left-hand side going up is the speed up. So how many times faster it's running against the sequential version. And as you can see, there's various different versions of the code. This might help address Costa's point about the program shaping. We've got 3 different lines here. The red line is a list version. It's actually the slowest. And the fastest version is if we do some program shaping to make it a binary, we actually get a much better speed up. So we go from 17 to 20 speed up, which is actually quite decent on 24 cores. It's actually an okay result. And when we used Lapedo to offload, we got something like over 200 speed up when we added a GPU. So something like going from 20 to 200 is absolutely massive speed up, just by introducing a hybrid skeleton and then allowing it to do the offloading for me. It's almost an order of magnitude better. Here's another example. So here, the dotted line here is the GPU and CPU version. This is the hybrid version. And the solid lines are the CPU-only version. So you can see here, the list version is actually pretty poor. So if I wasn't to do program shaping and introduce my binaries, I'd be kind of set at just over 1 speedup, which is absolutely rubbish. If I make things binary, it gets a bit better, but not really that much better. Something like a 6 speedup, it starts to tail off a bit. And then if I do an ETS, so if I introduce an ETS instead, it's actually a lot better. I do get quite decent scalability, about a speed up of 10 on 24 cores. What's interesting about this is that if we add a GPU, it's actually a lot better lower down the end here. So if I just look up to 12 CPU cores, and if I add a GPU, it goes from something like 7 speed up to about a 12 speed up. And if I look at the higher end, I think the best case is about a 13 speed up versus a 10 speed up, just by adding a GPU. So you get that slightly better performance. It could be that the best case might be to use this point here, a GPU, and then turn off a couple of the CPUs, because we don't need them. So there's no point having them switched on. We could then use them for something else, save energy, or use them to compute some other part of the problem. And then the final version, this is slightly different. So the hybrid version here is the brown line. And we've got 2 CPU-only versions, the red and the blue. The hybrid version actually performs quite considerably better. So something like from a 10 speed up to a 18 speed up, just by adding a GPU. So, just to start concluding, so what I've introduced is a framework called Lapedo. So this is a framework that allows, it helps you to write applications for heterogeneous systems, so systems comprising CPUs and GPUs, or CPUs and accelerators. And we have refactorings that automatically introduce the skeleton and the accelerator code into the Erlang file automatically. We have automatic generation of all of the offloading computations and data transfer boilerplate codes that will generate all of that for you. We've got pretty good speedups for a number of use cases we've got at the moment. We're currently writing a paper about this, so if you want to know a lot more detail about this work, I'm happy to provide you with copies of that. So that in the future, we've got quite a few things we need to start thinking about. One thing is this generating these kernels. So at the moment, I've kind of said, well, the user has to provide this. We're not thinking that this is a long-term thing. Once we've figured out how to generate these things, we will add that in. And also integrate more complex mapping mechanisms. So things like, how do we know how many CPUs to use and how many GPUs to use? And how do we know which pattern that we're supposed to use? Should we use a farm, or should we use a different type of farm? So we're currently looking at heuristics and machine learning mechanisms to deal with that. So the idea is a machine learning mechanism will tell you the most optimal configuration, the most optimal mapping, most optimal architecture, the best pattern to use if you give it an application. We're looking at a lot more realistic use cases, so we're looking into this, and we've got a lot more patterns to consider, so not just farms and pipelines, which are kind of the most simplest cases of pattern. And just a kind of a throwaway slide at the end. We need people to help us with this. So if you want to help us, please contact us. The Lapedo and Rephrase, which is an EU project that's supporting this work, you can join us on a mailing list which is provided here. You can get things like news, access to all of our software. You can get updates. You can chat to us. You can come to our workshops. We have tools for Erlang and some other languages as well. So feel free to help us in any way you can. But we'd really love to hear from you. And that's all I wanted to say. So thank you very much for listening.
And we have time for a few questions.
I don't sound critical, but if you look at the speedups you show,
Yes.
so you need to compare to get any. So let's take the previous one. I think it's more interesting. So this one, if I understand correctly what's happening, and I think I do, is that you are comparing something which is entirely in Erlang with something that is also has some Opencl code.
Yes.
Okay, so this is starting to comparing apples and oranges because you have to show what the Opencl code alone will be doing. So also, if you look closely here, the speed up you get, the speed up curve that you get in Erlang is pretty good, while the other one already starts with something that is up in the 9 range. So what would happen, for example, if you had here a machine with 64 cores? Perhaps the Erlang version could have been better. I don't know.
Or perhaps it goes down like that.
Or perhaps it goes down. I don't know.
Okay,
I guess the point is, why would an Erlang program, in this particular one, perhaps in the other ones it might be a point, but in this particular one, it looks like Erlang is pretty good, actually.
Okay, can I answer your points? Okay, there's basically 2 questions. So the first question is, why are we comparing Opencl to Erlang? Because Opencl is obviously much, much faster than Erlang, so it doesn't make any sense to compare that. I'll actually argue that that's not what we're doing. The point of what we're doing is to use Erlang because it's nice and high level. So writing code in Erlang is much simpler than writing code in Opencl. At the moment, a programmer has to provide a kernel, and we understand that that's not a very good solution. So we're looking into ways of generating that automatically from an Erlang function. So the idea is a programmer would use Erlang, which is nice and high level. He would express his algorithm, and then it would generate an Opencl kernel, and then it would allow you to offload. Okay. So the programmer doesn't have to learn any C, doesn't have to learn any Opencl. He's kind of in his nice high-level language, which is one huge advantage, I think. The second point, I'm not quite sure exactly what your point was, but you're saying if we can add an infinite number of cores, well, okay, 64, then it might go up. Well, it might go down. Also, the point on this graph is, if you look here, okay, that's not quite as good. But let's say I just pick this point. I can turn off all of these cores. I can almost turn off half the amount of cores that I'm using on my system and use them for something else. So why would I use that point when I can use that point? Doesn't make any sense. Well, okay. Yeah, which is saving huge amounts of energy, right?
So I was just going to follow up on Kostas' point, which is obviously we haven't tried this on 64 cores. You can't really project up from these graphs 64, maybe we can do that. But no matter where you are in this, you're getting benefit from using the hybrid approach. The GPU is always adding, and it is extremely unlikely, in fact, almost impossible, that you will never get some benefit. The reason why you're not getting as much benefit from the GPU as we're scaling up the number of cores is the work is diminishing Costas. So actually what's happening is more of the work is being mapped onto CPUs, less of it's being done by the GPUs. So there's a bit of balancing, dynamic balancing happening between the systems. But if you have a larger application, then the GPU is just going to keep adding to the performance.
I'm actually disagree with your previous point that Erlang is a nice language for technical computing or numerical computation, because in my opinion it was much better to use some kind of DSL, MATLAB-like or Julia-like style DSL for describing actual computing tasks, and then make Erlang scheduling this.
Okay. So I mentioned we have this framework implemented for other languages. So if you don't like Erlang, just use it for a different language. The framework here is completely generic. It's not tied to Erlang in any way. So if you don't like Erlang, just don't use it. Is my answer.
Final question.
I've got some existing CUDA kernels. Could I use them with this framework? Or
Yes.
is it limited?
Yes. So you can use them in a number of ways. So you can either provide the CUDA kernel. CUDA's a bit different because we don't have bindings yet for that. But it wouldn't be a very difficult thing to add bindings for CUDA. So you can either just provide the kernels directly and then use Erlang to do all the coordination at a high level. You can also then, if you want to, you can provide Erlang implementations of your kernels as well, and then try and get a mixture of using all the architecture. So you can either just provide the kernels and use your GPUs and use the hybrid skeletons to do the coordination, or you can try and use both of the things. Yeah, so yes.